Welcome back to QHSE Talks. Let me start with something uncomfortable, but necessary. Most serious fall incidents don't happen during extreme work. They don't happen on dramatic job sites or rare high-risk tasks. They happen during routine work, the kind of work people stop thinking about. A quick climb, a familiar stairway, a ladder you've used 100 times before. And that's exactly why Chapter 29 matters. Walking and working surfaces sit at a dangerous intersection of engineering, behavior, and physics. They look simple, they feel ordinary, but when they fail, or when we misuse them, the consequences are immediate and unforgiving. From a CSP perspective, this chapter is foundational. Under CSP Blueprint 11, this content primarily aligns with Domain 1, Advanced Application of Safety Principles, specifically evaluating common workplace hazards like falls, evaluating equipment such as ladders and scaffolds, and evaluating facility life safety features, including load capacity and surface design. But it doesn't stop there. This chapter also reaches into Domain 6, Occupational Health and Applied Science, because falls are not just policy failures, they are physics problems. Gravity does not negotiate. Reaction time does not improve under stress, and no amount of training can overcome poor engineering. That's why the emphasis here is not just rules, but controls. Not just compliance, but design intent. Guardrails instead of harnesses. Proper ladder angles instead of recovery reactions. Load ratings instead of assumptions. In other words, fall prevention before fall protection. If you're preparing for the CSP exam, this chapter tests your ability to recognize when an exposure exists, select the highest order control available, and understand why OSHA requires specific dimensions, loads, and configurations. If you're a practicing safety professional, this chapter forces a harder question. Are your walking and working surfaces designed to tolerate human error, or do they rely on workers being perfect? Because perfection is not the control. And that brings us to where we're going next.
So let's get into it. The source text, Yates's 4th edition, aligns this chapter with 29 CFR 1910. It covers a lot of ground. We have general requirements, ladders, step bolts, stairways, dockboards, scaffolds.
And the big one, the duty to have fall protection.
It is a wide net.
It is. Basically, if it separates you from the earth beneath your feet, it is in this chapter. And the goal is to understand the engineering controls that keep that separation secure.
Let's start with the most common tool on that list, the ladder. I feel like the ladder is the most disrespected tool in the shed.
Oh, without a doubt. Everyone has one. Everyone thinks they know how to use it. And yet, statistically, we are absolutely terrible at using them safely.
We really are.
And the disrespect comes from familiarity. We don't fear ladders because we grew up with them, but the regulations and the physics are very specific. The text breaks them down into two main categories, essentially. Self-supporting and not self-supporting.
Which is really just the technical way of saying step ladders and extension ladders.
Exactly. A step ladder is defined as a self-supporting portable ladder. It's non-adjustable in length, has flat steps, and a hinged back. It creates its own geometry for stability.
It stands on its own.
Right. An extension ladder or a portable ladder in some contexts is non-self-supporting. It relies on a structure to lean against.
The text mentions materials too. Wood, metal, fiberglass. Is there a functional difference in safety there, or is it just preference?
Oh, it's huge for safety depending on the environment. Absolutely huge.
Okay, how so?
If you are working near electricity, you absolutely cannot use an aluminum ladder. It is a conductor. You need fiberglass or, maybe a specially treated wood ladder.
So that's a life or death choice right there.
It really is. But fiberglass has its own issues. If you leave it out in the sun, the UV radiation breaks down the resin. You get what's called fiber bloom, where the glass fibers start to poke out.
I think I know what you're talking about. It feels like tiny splinters.
It creates a structural weakness, and on a practical level, it is incredibly itchy and painful to handle.
That is a good tip. If your ladder makes you itch, it might be time to retire it.
Yeah, that's actually a pretty good rule of thumb.
But let's get to the aha moment I had while reading Table 29.1 in the text. The duty ratings. I think most people assume a ladder is a ladder. But there is a hierarchy here that is critical.
This is where most homeowners and honestly a lot of professionals get into trouble. The duty rating isn't just a suggestion or a marketing term. It is a tested weight limit. And you have to understand what load means.
It's not just your weight.
No, it is not just your naked body weight on the scale in the morning.
Right. It's the total working load.
Exactly. It is you. Plus your heavy steel toe boots, plus your heavy winter coat if you're working outside, plus the tool belt with the hammer and wrenches, plus the drill you are holding.
Plus the bucket of paint you're carrying.
All of it. It adds up so much faster than people realize.
So let's break down the table because the naming convention is a little confusing. It starts at the bottom with Type 3.
Type 3. This is classified as light duty. The capacity is 200 pounds.
200 pounds.
Yeah.
I'm a fairly average-sized guy, but if I put on work boots and grab a toolbox, I am dangerously close to or over 200 pounds.
Oh, for sure. Honestly, in an industrial setting, a Type 3 ladder shouldn't even be on the site.
Really?
That is a household ladder. It is for changing a light bulb in the hallway or dusting a high shelf. It is not for work.
Then we step up to Type 2, medium duty.
Type 2 is rated for 225 pounds. This is often associated with commercial painters or a handyman. It is better, but it still doesn't leave a lot of margin for error if you're a larger individual or carrying heavy materials.
Okay, now we get to Type I. And logically, Type I sounds like it should be the top tier. We're number 1, right?
You would think so. It's totally counterintuitive, but Type I is just heavy duty. It is rated for 250 pounds. This is the standard industrial ladder you see on most job sites.
So this is kind of the baseline for professional work.
It's solid. It gets the job done for most general tasks. But if you are a big guy with a heavy demolition hammer, you might overload it.
Because above Type I, we have the superclasses. Type IA.
Type IA. Extra heavy duty, 300 pounds. Now we are talking about a serious tool. This is for rigorous industrial use where heavy loads are expected.
And the absolute top of the food chain.
That would be Type IAA, special duty, 375 pounds. This is a beast.
Wow.
If you are carrying heavy stock or if the worker is a large individual with full gear, this is what you need. There's no room for guessing.
The text emphasizes that these ratings are on the warning labels. But how often do you see a ladder where the label is covered in paint or drywall mud or just peeled off from sun exposure?
All the time. All the time. And the rule is simple and strict.
Yeah.
If the label is illegible or missing, the ladder is effectively unrated. You cannot use it.
You can't just guess.
No. You can't just guess that it looks like a Type IA. You have to remove it from service immediately. Tag it out.
That seems strict, but I guess if you don't know the limit, you don't know when it will fail.
Precisely. It becomes a blind gamble with your safety. And it's a gamble you will eventually lose.
Let's move to the usage rules. We have the right ladder, we've checked the weight, now we have to set it up. There are 2 geometric rules in the text that seem to be the golden rules of ladder safety.
The 4-to-1 rule and the 3 feet rule.
Let's decode the 4-to-1 rule first.
This applies to those non-self-supporting ladders, the ones leaning against a wall. The physics problem here is preventing the bottom of the ladder from sliding out. This is fundamentally a friction calculation.
Okay, so how do we calculate it? It sounds complicated.
It's actually super simple to remember. The rule says, for every 4 feet of vertical height, and that's specifically measuring from the ground to the point where the ladder touches the support wall, the base of the ladder must be placed 1 foot away from the wall.
Okay, give me an example. So if I'm climbing up to a roof that is 20 feet high.
You take 20, divide it by 4, and you get 5.
So 5 feet.
You need to pull the feet of that ladder exactly 5 feet back from the wall.
What happens if I cheat? What if I only pull it back 2 feet? It feels more stable because it's steeper.
It feels more stable, but it's not. The angle is too steep. You risk the ladder tipping backward, looping over because your center of gravity pulls it away from the wall as you climb.
You basically pull the ladder on top of yourself.
Exactly. It's a classic mistake.
And what if I pull it back too far? Say, 10 feet back, make it really shallow.
Then the angle is too shallow. The force vector pushing down on the feet isn't strong enough to generate the friction needed to hold it in place. The feet shoot out backward, the top slides down the wall, and you ride the ladder down face first into the ground.
That visualization is terrifying. So the 4-to-1 ratio sits right in the Goldilocks zone of physics, where friction and gravity work together to keep you stable.
Exactly. It balances the forces perfectly. It creates the optimal angle of about 75 degrees.
Now, the 3 feet rule,
Yeah.
this is for when you are actually getting off the ladder onto a roof or a platform.
Right.
The rule states that the side rails must extend at least 3 feet above the upper landing surface.
Why 3 feet? Is that arbitrary? Or is there a reason for that specific number?
Not at all. It is pure biomechanics. Think about the moment you step off a ladder onto a roof. You are transitioning from climbing using your hands and feet vertically to walking horizontally. That transition is the most unstable moment in the entire process.
You need a handhold.
You absolutely need a handhold. So the rails are there to grab onto. You hold the rails, you swing your leg over, and you are stable.
Ah, I see. If the ladder stops flush with the roof line, you are forced to crawl on your hands and knees.
You're grabbing at shingles or gravel or a slick metal parapet. You have no leverage. That is when people fall. It's a horrible, awkward movement.
It effectively extends the structure of the ladder past the danger zone.
Correct. It allows you to maintain your balance until your feet are firmly on the flat surface. It makes the transition safe.
Despite these rules, the text lists several common causes of accidents, and a lot of them seem to boil down to human impatience.
Impatience and overconfidence. Overreaching is the classic one. You're on the ladder, painting a wall. You need to reach a spot just 6 inches to your left. The correct procedure is to climb all the way down, move the ladder 2 feet, and climb all the way back up.
Which takes time and effort. Nobody wants to do that.
Exactly. So instead, you keep your feet planted and you lean, you stretch. The problem is you are shifting your center of gravity.
And there's a rule for that too, isn't there?
Yeah, we call it the belt buckle rule. As long as your belt buckle, your center of mass stays between the 2 side rails, the weight is driving down into the feet of the ladder.
But the moment that belt buckle crosses the rail,
You have created a lever. Your weight is now outside the base of support. The ladder spins or slides laterally, and gravity takes over. It happens in an instant.
another big one mentioned is carrying tools.
3 points of contact. That is the mantra. 2 hands and 1 foot, or 2 feet and 1 hand, must always be in contact with the ladder.
You cannot maintain 3 points of contact if you are carrying a drill in one hand and a paint can in the other.
No, you're down to 2 points. You're basically free soloing with a handicap at that point. You need a tool belt, or you need to use a haul line to pull the gear up after you get stabilized at the top.
And the final point on ladders inspection. The text says, before each use. That feels like a regulation that gets ignored a lot. I used it yesterday, it's fine.
That is the mindset that gets people hurt. A ladder can be damaged in seconds. Maybe someone dropped a hammer on the rail. Maybe a forklift bumped it. If you don't look, you don't know.
What are you looking for specifically?
Split rails, broken rungs, bent components, missing feet, anything that compromises its structure. And the text is explicit about what to do if you find a defect. You don't just put it back in the corner.
You have to tag it.
You have to immediately mark it dangerous, do not use. You have to take it out of service. If you just lean it against the wall, the next guy, who might be in a rush, is going to grab it. You have to physically segregate it or destroy it to prevent the accident.
Let's shift gears. We've climbed the ladder, now let's take the stairs. This section of the chapter fascinated me because we take stairs for granted. We treat them like the floor. But the engineering requirements for a staircase are wildly different from a hallway.
Oh, they have to be. Yates points out a really surprising fact here. Most structures are designed for a static load, the weight of the furniture and the people just sitting there. But fixed stairways are designed to carry 5 times the normal anticipated live load.
5 times. That is a massive safety factor. Yeah. Why the overkill?
It is not overkill, it is dynamics. Think about how you use a hallway. You walk. It is smooth. Now think about how you use stairs. You descend. You are essentially falling in a controlled manner from step to step. You land on each tread.
There's impact.
There's impact. And sometimes you run, sometimes you're carrying a heavy box, sometimes a fire alarm goes off and 50 people are stomping down that stairwell at the same time in a panic.
Okay, see?
That creates a dynamic load that is exponentially higher than just static weight. The structure has to be able to take that pounding without flexing or failing. The text also mentions a minimum load of 1,000 pounds.
The stomp factor, I like that. The text also gets into the geometry of the stairs, the rise and the tread. Table 29.2.
This is pure ergonomics. It's fascinating. There is a specific relationship between how high a step is, the rise, and how deep it is, the tread run, and it changes based on the angle of the staircase.
The text lists angles between 30 and 50 degrees.
Right. If you have a steep staircase, say 45 degrees, you need a shorter tread and a higher rise. The text says 8 3/4 inches for both. But if you have a shallow, lazy staircase at 30 degrees, you need a long tread, 11 inches, and a short rise, 6.5 inches.
Because our stride length changes.
Exactly. Your brain is wired for a certain gait. If you mess this up, if you put a steep rise on a shallow angle, people will trip constantly. Their feet won't land where their brain predicts they will.
That predictive processing is powerful. It's why you always trip on that one uneven step in an old house. Your brain measured the first step and put the rest on autopilot.
And consistency is actually a regulation. The variation between steps can't exceed a tiny fraction of an inch. If one step is an inch taller than the rest, it is a guaranteed trip hazard.
What about handrails? I see stairs without them sometimes. What's the rule?
The rule is based on the number of risers. If you have 4 or more risers, which means at least 3 treads, you need a handrail.
So a little 3-step porch might be exempt, but anything bigger needs a rail.
Correct. And the placement is specific. If it is an enclosed stairway walls on both sides, you need at least one handrail. The preference is on the right side descending.
Why the right side?
It's a simple ergonomic calculation. Most people are right-handed, and you are statistically more likely to fall while going down than going up.
So the force is pulling you forward.
Yes. So we put the rail where your dominant hand can grab it during the most dangerous movement.
That is a level of detail I didn't expect.
It's all about anticipating failure. If the stairway is open, you need rails on the open sides to prevent falling off the edge. And here's a detail for the wide staircases, like you see in a fancy hotel lobby or a big auditorium. If the stairs are wider than 88 inches,
That's a little over 7 feet.
you need an intermediate handrail, a rail right down the middle.
Because if I trip in the exact center of a 10-foot wide staircase, the side rails are 5 feet away. I can't reach them.
Exactly, you'd be tumbling with nothing to grab. The regulations are trying to ensure that a handhold is always within reach. The height is also regulated. It must be between 30 and 34 inches from the tread surface.
So it's not too low to trip over and not too high to reach comfortably.
Precisely. It's all designed around the average human form.
Okay, let's move to section 4. Dock boards and scaffolds. Dock boards, or bridge plates, seem simple. It is a metal plate bridging the gap between a warehouse dock and a truck. But the text treats them like loaded weapons.
Because they are deceptive. A dockboard looks like a floor, but it is a movable temporary bridge. The biggest danger is separation.
Separation.
Imagine a forklift driving onto the plate. As the wheels hit it, the force pushes the plate forward. Or maybe the truck driver thinks he is done and inches the truck forward. If that plate isn't secured, it slides into the gap.
And the forklift falls into the hole.
It is a crushing hazard. It's a horrific type of accident. That is why the text mandates anchors or anti-slip devices. You cannot just lay a piece of metal down and hope for the best. It has to be physically prevented from moving.
And then we have scaffolds. This is a massive topic in construction. We could do a whole deep dive just on scaffolds, but Yates highlights the basics. The foundation seems to be the critical point.
It all starts at the ground. You will hear the term mudsill.
I love that term. What is it?
A scaffold leg is basically a steel pipe. If you put a steel pipe on dirt or grass and put 1,000 pounds on it, what happens?
It acts like a cookie cutter. It punches right into the ground.
Right. It sinks. And if one leg sinks and the others don't, the tower tilts. If it tilts enough, it topples. So you use a base plate, a metal square, and you put that base plate on a mudsill, which is usually a large piece of lumber. It acts like a snowshoe.
It spreads the weight over a larger surface area.
Exactly. You can't build a safe tower on a sinking foundation. It's the most important piece.
The text also talks about the planking. I've been on some sketchy scaffolds where the wood looked like scrap lumber.
That is a violation. Scaffold planking is a specific grade of wood. It's engineered for that purpose, and the placement matters. The gaps between planks, it can't be more than 1 inch.
So you don't step through.
And so you don't drop tools through. A screwdriver falling 40 feet is a missile, we'll get to that. And you have to watch the overlap. The planks need to overlap at least 12 inches over the supports.
Why 12 inches specifically?
If the overlap is too short and you step on the very edge of the plank, it can seesaw. It tips up and you fall through. The 12-inch overlap ensures there's enough weight on the support side to keep it stable.
Again, it is simple physics waiting to punish a small mistake.
There is also a height ratio mentioned at the 4.1 ratio for tip.
This is different from the ladder 4.1 rule.
Yes, completely different application. This is about the dimensions of the scaffold tower itself. If the tower is 4 times higher than its minimum base width, it is considered unstable.
So if the base is 5 feet wide and I build the tower 25 feet high,
That is a 5.1 ratio. It is too tall for that base. You are at risk of tipping over in the wind or from the movement of workers on top. You have to install guys, ties, or braces to anchor it to the building or the ground. You have to artificially widen the base of support.
Okay, we've talked about the equipment. Now I want to get to the part of the source material that really stopped me in my tracks. Section 5, the physics of a fall, the math.
This is where we quantify the danger. It is one thing to say falls are bad. It is another to look at the numbers.
The text introduces the constant for gravity.
$9.88 meters per second squared, or 302.2 feet per second squared.
I want to pause on squared. That means you don't fall at a constant speed. You are accelerating. Every second you are in the air, you're getting faster.
Exponentially. It's a terrifying concept.
Let's walk through example 27.2 from the text. It fits perfectly here. We have a maintenance technician on a catwalk. He drops a wrench. The drop height is 5.5 meters. That's about 18 feet.
A standard industrial height. Not a skyscraper, just a second-storied catwalk. Very common.
So we want to know, how fast is that wrench moving when it hits the ground?
Right. So we use the formula VF2 equals V2 plus 2 of 10. Final velocity squared equals initial velocity squared plus 2 times acceleration times distance.
Okay, let's plug it in. Initial velocity squared is 0 because he dropped it, he didn't throw it.
Correct. Acceleration is $9.08 meters per second squared. Distance is $5.55 meters. So we multiply 2 times 9.8 times 5.5.
That gives us 107.8.
Right. So the velocity squared is 107.8. To get the final velocity, we take the square root of that number,
Which is?
10.38 meters per second.
Okay, that number doesn't mean much to me. For those of us driving cars, what is that in miles per hour?
It is about 23 miles per hour.
23 miles per hour. Okay. Added someone throwing a solid steel wrench at your face at 23 miles per hour.
It is not a bump. It is a bone-breaking impact. If that hits an unprotected head, it is a skull fracture. It is likely fatal. And remember, that was only an 18-foot drop. Imagine a 50-foot drop.
The text also mentions the time of the fall. How long does the person below have to dodge?
So we use the time formula. Dollars a dollar, VIO T plus 0.5 at T22. For that 5.5 meter drop, the time is roughly 1.06 seconds.
1 second.
1 second. And human reaction time just to see the object and process, oh no, is about 0.2 to 0.3 seconds.
So you're left with less than a second.
That leaves you less than 0.7 seconds to physically move your body out of the way, which is basically impossible.
You cannot dodge gravity.
You can't. By the time you hear the yell, it has already hit you. This is why hard hats are mandatory. This is why tow boards, those 4-inch barriers on guardrails, are mandatory. You have to stop the object from falling because you cannot stop the damage once it is in the air.
That brings us to the regulatory hammer, Section 6. The duty to have fall protection. OSHA isn't asking nicely anymore.
No, this is not a suggestion. 29 CFR 1910.28. The employer has a duty to provide fall protection. It is a mandate.
And there are magic numbers here, thresholds. And I know for a fact that this trips up people on the ASP and CSP exams constantly. The difference between general industry and construction.
This is the classic trap. You have to know which standard you are working under. It's a critical distinction.
So what are the numbers?
If you are in general industry, that's the 1910 standard fall protection kicks in at 4 feet.
4 feet? That's not very high.
No. If you fall 4 feet, you can easily break an ankle, a leg, hit your head. It's a serious fall.
Okay, and for construction?
If you are in construction, the 1926 standard fall protection kicks in at 6 feet.
Why the difference? Is gravity weaker on a construction site?
No, gravity is the same everywhere, unfortunately. The difference is historical and operational. Construction sites are dynamic, constantly changing environments. General industry, like a factory floor, is usually static. But practically for the exam and for compliance, you just need to know the rule. 4 feet versus 6 feet.
So if I'm a factory manager and I have a maintenance platform that is 5 feet high.
You need a guardrail. You are over 4 feet, no question.
But if I'm a framer building a house and I'm standing on a wall 5 feet high.
You are technically compliant without a harness because you are under the 6-foot construction threshold. Though, frankly, falling 5 feet can still mess you up pretty badly.
We mentioned falling objects with the wrench. What are the layers of protection there?
It is a hierarchy of controls. First, wear a hard hat. That is your last line of defense, your personal protective equipment.
Okay.
Second, use engineering controls like tow boards to prevent things from sliding off in the first place. Third, if you have heavy activity above, use screens or debris nets. Fourth, you could use a canopy structure to deflect falling items.
And the simplest one?
The simplest one is an administrative control. Barricade the area below, keep people out of the drop zone. If no one is there, no one can get hurt.
It is Defense in depth.
Yeah.
You need multiple layers.
Exactly. You can't rely on just one.
We are coming into the home stretch here. We have the gear, the physics, and the rules. But none of it works without Section 7, training.
Absolutely. 29 CFR 1910.3, the standard is very clear. You cannot send a worker into a fall hazard zone without training, and it has to happen before exposure.
You can't learn to swim after you've fallen off the boat.
That's a perfect analogy. And it is not just, hey, be careful, don't fall. The training has to cover the specific hazards of that area. It has to cover the specific equipment. If you hand someone a harness a personal fall arrest system, and they don't know how to inspect it or put it on correctly, it is useless.
Or worse, dangerous. I've heard if you wear a harness too loose and you fall, the straps can cause massive internal trauma when they snap tight.
That's right. And then there's suspension trauma, which is a real killer. If you are hanging in a harness for too long after a fall, the blood pools in your legs. It can stop your heart.
So training has to cover rescue plans too.
It has to. You can't just leave someone hanging there. You need a plan to get them down quickly and safely.
And training is no one-time thing, is it?
No. Retraining is required if things change. New hazards, retrain, new type of scaffold, retrain. And this is key. If the employer sees a worker messing up.
You mean like actively violating the rules?
Yes. If I see you climbing a ladder with a coffee in one hand, I have a duty to retrain you. I have to verify you understand the rules, not just punish you.
This leads to the final concept, the competent person. This is a capitalized term in the regulations. What defines a competent person?
It is a two-part definition, and most people forget the second and most important part. Part 1. They must be capable of identifying existing and predictable hazards. They have to know their stuff.
They need the knowledge.
Right. But here's part 2. They must have the authorization to take prompt corrective measures.
Meaning they can shut it down.
Yes. You can have a PhD in structural engineering, but if the boss says you are allowed to stop the work, you are not the competent person under OSHA. You need the power to say, stop. That scaffold is unsafe. Nobody goes on it until it is fixed.
That authority is what saves lives. It's the real power behind the title.
Absolutely. It's non-negotiable.
We have covered a massive amount of ground. We've gone from checking ladder labels to calculating impact velocity.
It's a heavy chapter in every sense of the word.
If the listener takes away just 3 things from this deep dive, what should they be?
Okay, 3 things. First, respect the ladder. Check the duty rating. If you are a pro, don't use a Type 3 household ladder. Get a Type I or IA. Use the 4-to-1 rule.
Got it. Number 2.
Second, respect the stairs. They are engineering marvels built for 5x the load because dynamic forces are violent. Use the handrail, especially going down.
And number 3.
Third, respect the physics. Gravity accelerates. You have 1 second or less to react to a fall. You cannot rely on your reflexes. You have to rely on the guardrail, the harness, and the training.
And for the exam takers out there,
Memorize the thresholds. 4 feet for general industry, 6 feet for construction. It will be on the test.
so here's the final thought, the so what. We talked about that 5x safety factor for stairs. The engineers build the staircase to handle 5 times the worst case scenario.
Right, to handle the panic, the running, the stomping, the unexpected loads.
So ask yourself, do you have a safety factor in your own work? When you are tired or rushing or frustrated, are you operating at 100% of your limit? Because if you are, a small slip means disaster.
That is profound. We need to build a behavioral safety factor into our lives. Leave yourself a margin for error. Don't work right at the edge of your physical or mental capacity.
Don't live life right at the edge of the cliff.
Because eventually gravity will test you. It tests everyone. You want to make sure you have that buffer when it happens.
A 5x buffer, ideally.
That would be nice, yeah.
This has been incredibly eye-opening, and thank you to everyone listening. Hopefully you'll look at that staircase a little differently tomorrow.
And check your ladder labels, please.
Definitely. Until next time, watch your step.